Dear students, welcome to EPG Pathshala. I am Dr. Rajkishore Sharma, an associate professor in chemistry department of Delhi University. Today we are going to discuss about the module X-ray photoelectron spectroscopy. We will discuss the data analysis part in this. This comes under the paper of Surface Analytical Techniques 2. Outline of the topic that we are going to discuss today: spin orbital coupling, chemical shift. Then we'll discuss multiplet losses, Plasmon losses, quantitative analysis, specimen properties, sputter yield and etch rate will also be discussed. We'll talk about sample depth, sampling depth and sputter profiles.
Now about spin orbital splitting. A doublet peak spectrum is observed for P, D and F subshells while singlet for S subshell due to the spin orbit coupling. After the photoemission of core electron, an unpaired electron left behind that has either a parallel or antiparallel orientation. Antiparallel orientation to the orbital momentum. There is an energy difference between parallel and antiparallel orientation. The energy separation of two adjacent peaks for the same orbit, that is, for same n and l value, increases with atomic number and decreases with the same n with higher L values. For example, the binding energy of magnesium of the 2p half and 2p 3 by 2 is practically same, that is 50 electron volt. While for silicon, there is difference of 1 electron volt for 2p half is equal to 2p half around 100 electron volt and for 2p 3 by 2 around 99 electron volt. The relative intensities of the doublet peak can be calculated using their degeneracy by using the formula 2j minus plus 1 by 2j plus 1. So just by putting j value in degeneracy formula, area ratio of the peak can be calculated.
Now about spin orbit splitting. Due to spin orbit splitting, doublet of P, D, F are obtained, but high total angular momentum state is found lower in energy. Other than this, elements present in different compounds have nearly the same splitting patterns as well as peak area ratios of an element in different compounds are also nearly the same. That is also makes XPS a very powerful surface analytical technique.
About electronic effect. This figure is for carbon 1s, that is for s orbital only. For s orbital, orbital quantum number will be 0 and spin will be plus half and minus half. So total quantum number j will be equal to half, whatever we consider, plus half or minus half. So we obtain only one value of total quantum number. According to degeneracy, peak will not split, as you can see from the figure. About electronic effect, the figure is for copper 2p, means for p orbital only. For p orbital, orbital quantum number will be 1 and spin will be plus half and minus half as usual. So total quantum number j will be equal to half and s will be minus half and 3 by 2. When s is plus half, so by using degeneracy formula, which is found equal to 2j minus plus 1 upon 2j plus 1, then peak area ratio can be calculated, which comes out to be 1:2, and you can see clearly from the figure that ratio of 2p 3 by 2 is almost twice than 2p half. Electronic effect of silver. Here electronic effect is shown for copper 3d orbital, means d orbital only. For d orbital value of L will be 2 and S will be plus half and minus half. So total quantum number will be equal to 3 by 2 and S is minus half and 5 by 2. When S is plus half, so by using degeneracy formula, for degeneracy peak area ratio can be calculated, which comes out to be 2:3. And you can see clearly from this figure the ratio of 2d 5 by 2 is 1.5 times than 2d 3 by 2. Figure shows the doublet for Ag 3d 3 by 2 and 3d 5 by 2 with the intensity ratio of 2:3. If shell is more than half full, then highest J lies lowest according to Hund's rule. Electronic effect is shown for gold 4f orbital. For f orbital, value of L will be 3 and S will be plus half and minus half. So total quantum number will be equal to 5 by 2 when S is minus half and 7 by 2 when S is plus half. So by using degeneracy formula, peak area ratio can be calculated, which comes out to be 3:4. Here you can see that from P to F orbital, the separation between two peaks is decreasing.
Now we will talk about chemical shift. The exact binding energy of an element depends not only upon the level from which photoemission occurs, but also depends upon the formal oxidation state and chemical and physical environment. The sample shifts in the peak in the spectrum is called chemical shift. Binding energy of an atom increases with the oxidation state due to extra Coulombic interactions between the photo-emitted electrons and the ion core. It is the major strength of XPS to distinguish between oxidation state and chemical environment. Chemical shift can also be explained by the effective charge potential change on an atom. For example, when an atom with small electronegativity makes bond with some high electronegativity atom, a charge transfer to the latter occurs and the effective charge of the former becomes positive. This leads to the higher binding energy of the former atom. From the figure, it can be seen that silicon is present in different oxidation state as lowest binding energy peak shows presence of Si2O with +1 oxidation state. Peaks around 104 electron volt shows SiO2 with 4 oxidation state. Thus, an atom with different oxidation state in a compound can be detected by measuring peaks at different binding energy.
XPS is able to give chemical state information about samples. Almost all elements in the periodic table exhibit a chemical shift, which can vary from a fraction of an electron volt up to several electron volts. The shifts observed in XPS have their origin in either initial state or final state effects. Now, what is initial state effect? It is the charge on the atom prior to photoemission that plays the major role in the determination of the magnitude of the chemical shift. For example, the carbon-oxygen bond CO in an organic polymer is shifted relative to unfunctionalized carbon-carbon by 1.6 electron volt. The more bonds with electronegative atoms that are in place, the greater the positive XPS chemical shift. For FC species, She is chemical shift being larger than those of CO compounds, as fluorine is more electronegative than more electronegative element. The CF group is shifted by 2.9 electron volt, whilst CF2 and CF3 functionalities are shifted by 5.9 electron volt and 7.7 electron volt respectively. An example of the electron peak fitting of a complex C spectrum, complex carbon spectrum for an organic molecule is shown in figure 11. By the consideration of the structure of the molecule, it is possible to build up a synthesized spectrum. The relative intensities of the individual components reflecting the stoichiometry of the sample. Now, about final state effects. Final state effects that occur following photoelectron emission, such as core hole screening, relaxation of electron orbital and the polarization of surrounding ions, are often dominant in influencing the magnitude of the chemical shift.
Now, the examples of chemical shift. Here are some more examples of chemical shift. One is ethyl tetrafluoroacetate, and other is the different binding energy of the carbon in ethyl tetrafluoroacetate that can be identified on the basis of chemical shift. In ethyl trifluoroacetate, from the 8th side of the first carbon is attached with 3 hydrogens, has lowest binding energy. Second carbon is attached with 2 hydrogen and 1 carbon and 1 oxygen. Thus, it has higher binding energy than first carbon. Third carbon is attached with 2 oxygens and 1 carbon. So, it will have higher binding energy than previous one because oxygen has more electronegativity than carbon and hydrogen. So that carbon has more polarity than others. Last one, carbon is attached with 3 fluorine atom and has highest binding energy. In other example, composite of molybdenum oxide and molybdenum sulfide is present, where molybdenum is present in different oxidation state. The intensity of molybdenum, second molybdenum 2 plus, is found higher because of highest amount of molybdenum is present in the sulfide form. But molybdenum in +6 oxidation state has highest binding energy.
Examples of chemical shift. In other example, composite of molybdenum oxide and molybdenum sulfide is present, where MO is present in different oxidation state. The intensity of molybdenum, second molybdenum 2 plus, is found higher because of highest amount of molybdenum is present in the sulfide form. But molybdenum in +6 oxidation state has highest binding energy.
Now, we will see what features can be seen in XPS spectrum. Sharp peaks obtained due to without energy loss means elastically scattered of photoelectrons created within the first few atomic layers. Satellite peaks are due to interaction of leaving electron with valence electrons and occurs in those metals which have high electron density near to the Fermi edge. Multiplet splitting, which occurs when unfilled shells contain unpaired electrons. Inelastic scattering covered with electrons emitted from solid surface reach to detector with some energy loss. Plasmon loss peaks arise when an outgoing electron excites collective oscillations in the conduction band electrons.
Satellite peaks without any monochromator source are well known and can be removed from spectrum using monochromatic X-ray source. Some satellite peaks arise when a core electron removed by photoionization. A sudden change in the effective charge is observed due to the loss of shielding electrons. The leaving electron interacts with a valence electron and excites it to a higher energy level. As a result of energy of core electron is reduced and satellite structure appearance few electron volt above the binding energy scale. These peaks are called shake-up satellite peaks. After ejection, the valence electron from the ion completely, it excites in empty state above the Fermi edge and appears as a broadening of the core level peak, and it happens in those metals which have high electron density near to the Fermi edge. Therefore, a tail on the high binding energy side of the core level peak is generated. Intensity of these peaks is found quite strong in case of transition metal and rare earth metals with unpaired electrons in the 3D or 4F shells. Figure shows the XPS spectrum of copper oxide and CuO and Cu2O. A strong shake-up satellite peak is observed in case of CuO, but almost negligible in Cu2O. This is due to the presence of unpaired electron in 3D orbital of CuO, while Cu2O has 3D10 configuration, means that all electrons are paired up. There can be coupling between the unpaired electrons present in the core level with the unpaired electrons in the valence shell, during photoelectron emission. This can create multiple splitting or number of final states that can be seen in the spectrum of the final state. Figure shows the multiplet splitting of 2p3/2 spectrum of nickel or nickel oxide, but not nickel hydroxide. That is a good characteristics of XPS in the examination of passive films of nickel. Plasmon losses are specific to clean metal surfaces. Plasmon loss peak arise when the outgoing electron excites collective oscillations in the conduction band electrons and thus suffers a discrete energy loss and observed as a characteristic series of peaks on the high binding energy side of the main core line. The characteristic peaks of clean aluminium are shown in figure. XPS is also used as a quantitative analysis of sample, but there are few factors related to sample and spectrometer. Sample related factors include cross section for the emission and the escape depth of the electron emitted from the atom. The cross section for emission is the probability of the emission of an electron from an atom due to the effect of the incoming radiation or X-ray photon. Cross section depends on the number of factors such as element under investigation, orbital form which electron is ejected, and the energy of the exciting radiation. In general, for XPS measurement, with increasing the atomic number, the cross section for photoelectron emission also increases for a given series of core levels such as 1s, 2p, etc. Spectrometer related factors include the transmission function of the spectrometer, efficiency of the detector, and effect of magnetic field. The transmission function is the proportion of the electron transmitted through the spectrometer as a function of their kinetic energy. This function depends upon the way in which the lenses are operated. Usually, this function is measured by the manufacturer and account is taken of it automatically when data are quantified using the manufacturer's data system. The mean of efficiency of the detector is that how many electrons are detected by the detector out of the total number of electrons strike the detector. The basis of XPS quantification is the determination of the intensity of a characteristic signal from a measured spectrum. The intensity of a photoelectron peak from a homogeneous solid is I is equal to J rho sigma K lambda, where J is the photon flux, rho is the cross section of the photoelectron production, sigma is the concentration of the atom or ion in the solid, lambda is the electron attenuation length, and K is a term that depends on instrumental factor. The above defined intensity will be taken as an integrated area under the peak following the subtraction of a linear S-shaped background. This above equation is called first principle approach because it can be used for direct quantification, but generally the experimental sensitivity factor will be used. The sensitivity factor includes the terms such as K, lambda in the standard equation, and all these terms are also incorporated into a set of sensitivity factor appropriate for spectrometer used. If X-ray flux or photon flux remain constant during the experiment, the atomic percentage of elements can be calculated by dividing the peak area represented by I by sensitivity factor, that is represented by F. The atomic percentage of the elements can be calculated employing the given formula. A, that is atomic percentage, is equal to IA upon FA into I upon F into 100%. The above method provides a valuable means for similar specimen because this method assumes that the specimen is homogeneous within the volume sample by XPS. For more rigorous analysis, angular dependent XPS may be employed to ensure lateral homogeneity and to elucidate hierarchy of overlayers present.
Now about specimen properties. Before analyzing sample using XPS, we need to know about the properties of sample, which are discussed here briefly. So, a prerequisite for a meaningful surface analysis is a stable surface with time. This means that analysis is restricted to solid surfaces with negligible vacuum pressure at room temperature. Liquid surfaces can be studied using a cooled stage. Inorganic matter, in particular metals and alloys, usually are easy to study with surface analysis because of their good electrical and thermal conductivity. In this respect, still tolerable are low band gap or doped semiconductors. Insulators may cause several problems with respect to charging. Polymers are also difficult to study sometimes because of charging, but most often because they tend to change their composition under electron or photon irradiation. The latter effect is particularly strong in biological matter, which often possesses an intolerable high outgassing rate. Usually, thermal effects caused, for example, by electron beam radiation are negligible in bulk metals, but it increases for insulators and organic materials. Knowledge of history of previous treatments is necessary to prevent the vacuum chamber and the analyst from hazardous materials. Now about size, shape and roughness. Other than properties of samples such as conductive, non-conductive, size, shape and roughness of the samples are also crucial part to determine before analysis of the sample. If size and shape of a material do not fit to the instrument stage, a specimen has to be cut by mechanical means. Of course, the maximum size depends on the sample stage. Usually 5 to 10 millimeter square and thickness up to several millimeter square are employed, but larger samples can be handled by special mounts up to diameter of the introduction flange. Irregular shapes can be handled by cutting off a part that will result in a flat bottom. Small samples can be mounted on a supportive sheet, for example, fixed with liquid silver or carbon, and powders can be pressed in a soft indium foil. Compact bulk material with a smooth surface is most desirable. Surface analysis of materials with rough surfaces may be divided in two categories. The one with macroscopic roughness in the micrometer range or above, where frequently fairly smooth microplanes occur, can be studied with high resolution AES or high resolution XPS. The other category are surfaces with micro roughness or nano roughness, where typically many different oriented microplanes contribute to the signal.
Sputter yield and etching rates are also important factor in XPS. Both terms are used during depth analysis of samples, so both are needed to be discussed. The mechanism of depth analysis is that electrons originating from deep within the sample suffer an elastic collision within the sample and are emitted from the surface at some large angle with respect to the surface normal. Because the scattering is elastic, the electrons contribute to the peak intensity. In the case of a thin oxide layer on a metal, the effect causes the signal from the metal to be greater than expected and can lead to layer thicknesses being underestimated. Now we will see what is sputter yield. Thus, the sputter yield is a physical property which determines the rate at which material is removed from the sample during bombardment by energetic ions. This is the physical property of a sample which has greatest influence upon the rate at which it can be profiled. To be of practical value, the sputter yield needs to be converted to an etch rate usually given in the units of nanometer per second. There are many factors which affects the etching rate such as ion current, ion energy and nature of ion beam. All are also discussed here. The sputter rate depends upon the chemical nature of the material, not only the elements present but also their chemical state. It is usually preferable to measure the sputter yield experimentally under the conditions normally employed. Now about ion current. The etch rate is directly proportional to the ion current. It is possible to increase the etch rate by using the maximum beam current available.
Now about sputter yield and etch rate. Another factor which affects etch rate of the sample is ion energy. The sputter yield increases with ion energy. Higher energies also mean smaller spot size at a given beam current, and so will lead to a better crater quality. The higher etch rate will be accompanied by proper depth resolution because the ions can penetrate deeper into the material causing atomic mixing. Nature of the ion beam in XPS and OJ profiling is it is customary to use the ions of the noble gases for sputtering. In practice, argon gas is used, which is selected. Thus, the ion current and nature of ion beam all are factors which affect etch rate effectively. Therefore, if there is a requirement of high etching rate, ion current must be high. If requirement of sputter yield is high, then energy of ion should be high. So all were inevitable factors which have to be discussed here briefly.
The need for accurate and precise measurements of metal oxide thickness is becoming even more crucial. There are a number of analytical techniques capable of measuring oxide thickness of films less than 10 nanometer thick. These techniques include XPS, AES, SIMS, TEM, nuclear reaction analysis, that is NRA, spectroscopic ellipsometry, and capacitance voltage measurement. Here, we are just discussing procedure for calculating the thickness of aluminum oxide. X-ray photoelectron spectroscopy and OJ electron spectroscopy, XPS and AES, offer precise measurements for ultra-thin, that is less than 3 nanometer film, but are limited for thicker films, that is those are higher than 15 nanometer, due to the exponential decay function that describes the sampling depth in both techniques. Usually, the binding energies of the oxide and the metallic species are separated by a few electron volts. Thus, when the oxide is thin refers to less than 9 nanometer, it is possible to distinguish the contribution from both oxide and metal photoelectrons. For aluminum oxide thickness, D is given as if the metal oxide ratio can be determined for a thin film oxide sample approximately 0 to 9 nanometer, and if the inelastic mean free path, which is abbreviated as IMFP lambda, of the metal, that is in lambda m meter, and oxide lambda metal lambda m, that is metal, and oxide lambda OX is known, the oxide film thickness can be calculated using the calculations of the type developed. For example, D in nanometer is equal to 2.8 ln 1.4 I naught upon Im plus 1, where I naught and Im are the intensities, or we can go with peak areas of the oxide and metal photoelectron peaks respectively.
Now about depth profiling. Sampling depth analysis can be achieved in three ways for both XPS and AES. These are as follows. Number one, by using the Beer-Lambert's equation, depth information can be achieved in a non-destructive manner. That is, by changing the geometry of the experiment or by changing the energy of emitted electrons. Number 2, by using ion sputtering method in alternative mode, by removing material from specimen then undertaking analysis and again removing materials and analysis. By etching material mechanically and examining freshly exposed surfaces is the third point. All above methods are applicable for X-ray photoelectron spectroscopy and in the same manner for OJ electron spectroscopy.
The information depth in XPS analysis is of the order of a few nanometers. If the electrons are detected at a direction normal to the sample surface, this is the basis for angle resolved XPS, AR XPS. This method can be applied to films which are too thin to be analyzed by conventional depth profiling techniques, or those that are irretrievably damaged. Such methods, this is for polymers. Another reason to use AR XPS is that it is a non-destructive technique which can provide chemical state information, unlike methods based upon sputtering. Another advantages of XPS is the depth analysis of sample. In this slide, we will learn what is sampling depth and how can we achieve this. So sampling depth is the depth from which 95% of the photoelectrons are scattered by the time they reach the surface. The Beer-Lambert's equation can be used in a variety of ways to provide to a non-destructive depth profile, that is, without removing material by mechanical, chemical or ion milling methods, and information about overlayer thickness. The depth of analysis in both AES and XPS varies with kinetic energy of the electron. The attenuation length, lambda, is used to calculate depth of analysis. It can be defined as the thickness of the material through which electrons may pass with the probability 1 upon E that they survive without inelastic scattering. It depends on material and electron energy. The intensity of emitted electron I from the depth greater than d in a direction normal or perpendicular to the sample surface given n by Beer-Lambert's equation, that is I is equal to I naught exponential minus d by lambda, where I naught is the intensity from an infinitely thick uniform substrate. For electrons emitted at an angle theta to the perpendicular of the specimen, this expression becomes I is equal to I naught exponential minus d by lambda sine theta. It can be understood by considering the depth d is equal to the 3 lambda sine theta. While XPS is a surface sensitive technique, a depth profile of the sample in terms of XPS quantities can be obtained by combining a sequence of ion gun etched cycles interleaved with XPS measurements from the current surface. An ion gun is used to etch the material for a period of time before being turned off while XPS spectra are acquired. Each ion gun etch cycle exposes a new surface and the XPS spectra provide the means of analyzing the composition of these surfaces. In this slide, it is clear that depth of the analysis is dependent on the electron angle of emission. As shown in figure, if the angle of electron emission is 30 degree, then analysis is recorded which is extremely surface sensitive and sample can be analyzed up to 5 nanometer. Thus, when electrons will emit normal to the surface, that is 90 degree, then d will be approximately 3 lambda or about 10 nanometer. The finite mean free path of electron within a solid means that the information depth in XPS analysis is of the order of a few nanometer. This of course is only true if the electrons are detected at a direction normal to the sample surface. If electrons are detected at some angle to the normal, the information depth is reduced by an amount equal to the cosine of the angle between surface, normal and the analysis direction. This is the basis of a powerful analysis technique, angle resolved XPS, AR XPS. One of the reasons of the usefulness of the method is that it can be applied to film which are too thin to be analyzed by conventional depth profiling technique, or those that are irreversibly damaged by such methods. Example, polymers. Another reason for XPS to use AR XPS is that it is a non-destructive technique which can provide chemical state information. Unlike methods based upon sputtering, you can see from the figure that intensity of oxide is high when we focused only on surface and we focus on bulk. Then intensity of the metal becomes high, which is the main application of AR XPS, that without damaging sample, bulk information about sample can be achieved easily.
Now, advantages compared with conventional approaches. Now we will have a look on comparison of AR XPS with conventional approach. So, AR XPS can be applied readily to large samples without the difficulties. Small area AR XPS is possible, but would be very difficult using conventional methods for the following reasons. First, at all angles, the analysis position would have to be accurately aligned with the feature to be analyzed. This is difficult, especially if the analysis position is at some distance from the tilt axis and required analysis area is very small. Second, the analysis area changes as a function of angle. A worst case occurs when the transfer lens is used to define the analysis area. Using parallel angle acquisition, the analysis area and position is completely independent of the emission angle. If an insulating sample is tilted, the charge compensation conditions also change. Changes in peak position or shape may then be due to the efficiency of charge compensation. Using parallel acquisition of angular data, the compensation conditions are the same for all angles, and any changes in the spectra as a function of angle must reflect real compositional difference.
Non-destructive methods are only for depth analysis up to 10 nanometer. To obtain greater than this is necessary to remove material by ion bombardment within the spectrometer. Sputtering is called destructive method. We can study depths of material in the range of 1 to 2 micrometer employing this technique. Generally, argon have energy of 1 to 5 kiloelectron volt is used to bombard the sample. Surfaces are sputtered away and residual surface is analyzed. The sputtering process is not so easy. There may be preferential sputtering of a particular type of ion or atom. From this figure, you can easily understand the destructive method for depth analysis. Firstly, sample surface can be analyzed using X-rays as primary source. Then for bulk analysis, surface is etched using argon ion sputtering. And again, we get XPS spectrum using X-rays and so on. In destructive method, high vacuum is very necessary because sputtering produces a highly reactive surface which can get residual gases from the vacuum. These contaminants can affect the analysis and may not reflect the material composition. Contaminants, oxygen, water and carbonous materials are very common. Thus, gas supply to the ion gun must be free from contaminants.
From the above discussion, we can conclude that peak area ratio of intensity can be calculated using 2J plus 1. If the shell is more than half full, then highest J lies lowest according to Hund's rule. Binding energy of an atom affects from the environment of an element present in the compound. We learned also about the shakes up satellite peaks. Multiple peaks and plasmon peaks emerges. In quantitative analysis, we learned how we can calculate percentage amount of a particular atom in specimen. Depth analysis of a sample can be studied in two ways, destructive and non-destructive. Using angle resolved X-ray photoelectron spectroscopy, depth analysis of a sample can be done up to 10 nanometer without etching of sample. To obtain greater than this, it is necessary to remove material by an ion bombardment within the spectrometer. Depth of the sample can be studied in the range of 1 to 2 micrometer using sputtering. Thank you.